Hello! Today I'm going to talk about analog television. It's really a shame that analog television has become obsolete because it was the apex of electronics technology. So many miracles had to come together to make it work, and it's just so fascinating to see how it was all done. And we're only going to talk about part of it. We're just going to talk about the basics of sending a picture over a wire electronically. And we're not even going to talk about television broadcasting. We'll get into that in the communications class down the road. So let's get started and find out how we took this journey to develop electronic television as we knew it in the analog age. So first of all, let's talk about movies, because they were a completely different technology, but it shows us some of the problems that we had to overcome to make television work. So to make a photograph, we simply have something that is photosensitive, a photographic plate, if you will. This could be film or whatever. And this is coated with a substance that is light sensitive that can be developed and create an image. So it was basically silver iodide, which was photosensitive. When a photon hits a crystal of silver iodide, it kicks out an electron and changes its chemical properties, and then we can bathe that in certain chemicals and cause that particular crystal to darken. And so if we do that in a pattern, which we usually do by using a lens to focus an image, I'll use my venerable candlestick as my object to focus. And so this goes through the lens. We talk about how that works when we talk about optics previously. And that forms an image, upside down, of course. And the dark parts of this picture will become the light parts, because remember, where the light hits it, this becomes dark, and where the light doesn't hit it, it stays light. And so we get a negative image that must be reversed by some kind of a printing process, or in slide and movie film, we get a direct positive after the developing. So if this was slide film, which simply makes a transparency, a color transparency in the later times, this would come out where the light parts would become light and the dark parts would become dark, and we end up with a permanent record. But it's all done at once. So we have a shutter that blocks off the light. We open that shutter, light goes through, we close it, takes a very short time, then we develop that and we have an image. So the image is developed on each individual crystal in this emulsion that is on the film. And of course, for moving pictures, we simply had a strip of film and took many, many pictures over and over again. Oops, if I can draw that properly. And this, of course, would have sprocket holes to allow the moving of the film through the projector, and we shine a light through it. That light goes through a lens and is projected on a screen or whatever we did. So the difference is here, of course, that each one of these images is taken in an instant and is recorded on thousands upon thousands of silver iodide crystals that through the developing process we extract some dyes from the film through chemicals I don't understand, but we get these colors that look pretty dang good compared to the original. And so we run these through, and so many per second. In the movie industry, that would be 24 frames per second, which would be just fast enough to keep it from flickering noticeably. And so that would save film. They could, of course, run it through faster and get less flicker, but film costs money, so they did the very slowest they could, which tended to be 24 frames per second. So that's your standard movie rate, which became a problem when transferring movies to video, which we'll talk about down the road. And so that's the idea of making a movie. Each shot is taken at once, recorded on thousands upon thousands of silver iodide crystals turned into colored dyes and projected one at a time at a speed of around, in the theaters, around 24 frames per second. Home movies would be much slower, maybe 16 frames per second. I don't know the exact numbers, but that's the way it worked. Now, how can we do this electronically? Well, it's not going to be as easy as just simply snapping a picture and sending it electronically, because we have so many of these little entities, these silver iodide crystals that carry this image. How can we send that electronically? We could have thousands upon thousands of wires and thousands upon thousands of photosensors and send that down that's not going to work. So we have to figure out a better way. And some people in the early 1900s came up with a way that sort of worked, and that was to have a spinning disc. So here is a disc, and that's spinning, and there are a number of holes in the disc. I think that was, of course, refined later on to, I'm going to make this crude here, later on was refined to a bunch of lenses, which of course were heavy and expensive. There were all sorts of problems with this, but the idea was to spin this disc and to focus the image. Of course, we don't have the film anymore, so let's get rid of that. So here is a lens, and here's the image we want to record. And so this disc is put in the path in such a way that it allows the light through as each hole goes by in succession. And the idea is that these are spaced such that by the time this hole goes across, so we have the light coming through that hole, through the lens, to a photoreceptor. So here's the disc, here's the image, and we're going to, let's figure out something here. There's more than one approach to this. We're going to focus that image on the rotating disc. Let's make that a little thinner, which is full of holes. And it's going to be probably another lens to focus what comes through down to a photo tube of some sort. This was, of course, done with vacuum tubes in the early days. So it would be a photo tube of some sort. And so as those holes spin by, this hole goes across the top of the image, then this hole goes by the next part, then the next hole goes across the next part. And so you see we get a sequence of light profiles for each one of these lines as the holes scan by. So now, as this scans across, we're going to get darkness, and then some light, and then some darkness. And as time goes by, we'll see the voltage coming off of this photosensor going up and down. So it's going to be low voltage, low voltage, low voltage, goes up and then down as it goes across the flame. And we're going to get the same thing with the next one. Let's just keep on going here. We'll get low voltage, low voltage, low voltage, bright as it goes across the flame, and then maybe a little bit as it goes across the wick. And so we get this long string of information that is these scan lines, if you will, put together. Now all we have to do is reverse the whole idea, where now we have a light going through the lens, focusing on a similar disc. And as that rotates, that disc, well, once again goes through a lens and then focuses the image, which is going to be just parts of the image: top of the flame, middle of the flame, bottom of the flame, bit of the wick, bit of the candle, all broken up. But of course, if you get these lines close enough together, you have maybe a fairly decent image. So this was a system that was predating electronic television as we know it. The most famous person known for developing this was John Logie Baird. I don't know why they always have to include his middle name, but that was it. And he developed this about as far as it could go, and they were using this system in England to transmit some crude television before fully electronic television came along as we know it today. Now along comes a 12-year-old farm boy in Idaho by the name of Philo Farnsworth. Now he's living on a farm that was electrified, which was not very common in 1918. Because of that and some equipment that had been around that he could tinker with, he developed a very strong interest in electricity. And in the attic of this house was a stash of scientific journals, and he was able to study these and learn a lot about electronics on his own. And so he used his knowledge to repair motors and such. He motorized his mother's washing machine and did some other inventing on his own for quite a young age. And he was aware of some of the developments of the time, so he knew what a cathode ray tube was. He knew some of the other developments in possibly trying to develop an imaging device for making television. So he knew that people were working on this, and he was trying to figure out how this could be done. And legend has it that while he was plowing a field, the back and forth motion, making the straight furrows in the field, gave him the idea of moving an electron beam in a cathode ray tube back and forth and up and down to put an image on a screen. So let's say we have a cathode ray tube, and he's credited with inventing this whole idea of taking this cathode ray tube, which has an electron emitter. We call them electron guns today. I don't know how primitive his was, but he had a cathode ray tube which emitted a beam of electrons toward a positively charged area where modern tubes have a coating of metallized material that can be positively charged that will attract that beam. But the momentum of the electrons carry them all the way to the front where the inside is coated with a material that originally contained phosphorus. They call it a phosphor these days because it may or may not contain phosphorus these days. And that would glow when the electron beam hit it. And it was already known in his day that you could use magnets. There's our north and south poles of a magnet to deflect that beam. And he's credited with the idea of using electromagnets. So I'll put some coils around here. And I believe, if I think about this right, I think a coil on the top and bottom can move the beam side to side, and other coils on the sides could move it up and down. And they were much larger than this. They covered a lot of the tube and wrapped around it, but the coils were arranged such that we could steer the beam back and forth and up and down with these coils. And he's credited with the idea, if we take this tube, we could scan that electron beam back and forth across the tube in order to create a picture. But a lot of things had to be done to develop this into a working television. So let's first start talking about some kind of an imaging tube. So this would be a display tube that could move that beam back and forth. And if we simply make the electron beam stronger or weaker, we can make the spot brighter and darker as it goes across the screen and actually paint an image on that screen using the electrons. But let's move to the beginning and look at creating some kind of a camera that could create something that could be sent to this CRT to create that image. And Farnsworth is credited with developing the first working camera tube, and that was called the image dissector. So basically what he had was a cathode ray tube that sort of worked in reverse. So here's the front of it, and it's kind of a squarish tube if the diagrams I've seen are correct. And he had a screen here of material. I don't know exactly what it was, except it was coated with cesium oxide. And so we put a lens here and focus our image. There's our good old candle there on that screen. I'm not going to show it, but the lens is going to focus that on the screen, and that's going to cause the cesium oxide to emit electrons. So we get a bunch of electrons out here, and wherever light hits the cesium oxide is going to emit more electrons, less light, less electrons. And he had something positively charged toward the back. Not sure exactly how it was arranged. I'll just show something around the tube here. And that would cause these electrons to stream backwards in a straight line. So if we put a phosphor screen at this end, we would make a faint image that was analogous to the image that was being created on the screen. Brighter light, more electrons, they would stream back, hit the phosphor, and we'd get it to light up. This is sort of what image intensifiers do today, if I understand the principle correctly. But he did not have an imaging screen back there. Instead, let's make a little room here. Somewhere in the back, I'll put it in the middle, he had a photosensitive tube, a phototube basically. And we put our magnets back around here. And basically he takes this whole image and steers it around back and forth and up and down. So if you can picture an image of our candle here, we're steering the whole image around so that only part of it enters. Put a little aperture here for our phototube, and only the electrons from a tiny part of the screen here would actually enter this phototube, and that would be taken out and processed through a lot of stuff I'll talk about in a moment to create something that could be reassembled in the cathode ray tube to be an image of what we have here. So that's kind of the cart before the horse, but that's the way the first image dissector worked. A big disadvantage to it was that all the electrons that were streaming away from parts of the image we weren't looking at were basically wasted, and we could only look at the electrons that were created in real time in this imager, and so it was not very sensitive, but it had the advantage of not saturating like some of the later tubes did. For example, some of the later tubes would saturate in such a way that we would end up with a black halo around bright spots, and that was something that had to be mitigated with later designs. But the image dissector was still used for many years in places where you needed to view very bright objects such as flames in a furnace or probably even jet exhaust, I don't know. But it did have a use, even though it was not very practical for broadcast TV. But that was the first idea of something that could create an image. So we have these electrons streaming back, which are analogous to our image, and we just simply steer that into our phototube. And Farnsworth did develop a better system that used a photomultiplier and gave a brighter image. But nevertheless, it still was not really suitable for broadcast TV. We needed something that was more sensitive. We had to have incredibly bright lights for this to work. They nearly incinerated these people in the studio with the lights necessary to make this work. So we needed something that worked a little better. So Vladimir Zworykin is credited with developing the iconoscope, which worked on a different principle. They had different shapes, but the original that's usually shown in diagrams is shaped sort of like this. We had an imaging plane here, and our electron gun was down here. And we had a window here basically, so this part of the tube was flat. Here is our lens out here, forming our image on this part of the plane. And this was coated with material that included silver but had other materials in it too. I think also had cesium oxide. And worked on a completely different principle. When they made it, by baking it in an oven, and this was actually discovered accidentally, with the right amount of heat, the material would crack into small parts, and with another material coated on the back, it formed little tiny capacitors that could store charge. So we have our image going in there, and first they would use the electron beam at high velocity, and they would scan across this to charge all those little capacitors, if you will, with charge. And then they would turn off the beam, and the light coming in would discharge some of those capacitors. The more light, the more it would discharge. So we ended up with an image on these materials that was less charge where more light hit. So it's kind of an electron negative image. So we had electrons on these capacitors, few electrons where a lot of light had hit, and more electrons where less light had hit. And then they would scan it again with low velocity electrons, and where there was a large charge here, those electrons would be repelled, and there was a ring of metal or something similar to that in the front that was positively charged that would attract those electrons away. So this beam comes and hits a place that had a high charge where little light had hit. Those electrons would be reflected away, picked up by this ring, and so we would have a lot of electrons reflected away where little light had hit. So a lot of electrons at dim areas, but at a bright area where a lot of electrons had been removed by the light, fewer electrons would be reflected off, so we'd get fewer electrons where there was a lot of light and more electrons where there was a little light, so basically a negative image. And this information was taken back and processed, inverted, so that we get more electrons where there was more light, fewer electrons where there was less light, and eventually create something that could be turned into a signal that our CRT could then paint our picture back with. And the iconoscope was later developed so that the electron gun was moved to the rear, and so it didn't have to be painted from the front. But the big advantage of the iconoscope was that it could store charge here, so that as the light hit the photosensitive pieces, they would store more and more charge, and so we weren't wasting that information, such as in the image dissector where we had the electrons coming back in real time. We were wasting electrons that could have been maybe stored to make a brighter image. So this stored up the charge, knocked it off, and was eventually taken away to make an image. So the next development after the iconoscope that was a major development was the image orthicon, which was a little more complex than I'm going to describe here, but I'll give it a quick go. Once again, it had the electron beam in the back, lens up here, the object to be focused, and it had a screen here. Behind that was another screen, and there's a little mesh in here to get the electrons to accelerate the right way, but I'm not going to get too deep into that. So we focus the image here, then we have those electrons accelerate away. Sounds a lot like the image dissector. And over here was a plate that had little areas that could charge up from these electrons hitting it. So then we send an electron beam, and it is deflected and made to hit this perpendicularly, so that when it hits these charged capacitors, if you will, causes them to lose their electrons, and those electrons will go, well, it's like, you know, if you hit it this way, the electrons are going to go that way. If you hit it this way, the electrons are going to go that way. But if you hit it straight on, the electrons will go straight back. And there's a high positive charge here. There's a little hole that the electrons are accelerated through. So these negatively charged electrons, you would think, would go to this positively charged grid here. But instead, their momentum carries them through. Then the magnetic fields deflect it, come in straight, and then those electrons that come back straight are attracted to this positive charge here. So they want to go back to that, and they follow the same path, basically, back because of the magnetic fields, and are absorbed by that positive grid, and that gives us voltages that we can use to send to the CRT to recreate the image. And finally, the Vidicon tube, which is, I'm really kind of surprised it wasn't one of the first developed, because when I thought of how would I make a picture camera, that was kind of the first thing I thought of. So we have a tube. Ones I've seen were pretty tubular. Here is a screen that is photoresistive material. In other words, in the dark, it's a high resistance. When light strikes it, it's a low resistance. And now we hit that with an electron beam, scanning across it. So once again, here's our lens and our object we are taking our image of. And where the light hits this photoconductive screen, it's going to be more conductive than where light doesn't hit it. So as this electron beam, once again with our coils, which, as I said before, really kind of go along the whole tube to give us lots of area to work with, but that beam is steered, and when it hits a spot where there's a lot of light hitting the photoconductive material, it's going to conduct a lot of those electrons away on a wire to the back of the tube, so we get a fairly high current. But if there's a darker area, we get a lower current. So we get a current going to the back of the tube that's proportional to the light hitting the screen. And I think there's got to be something in there to pull away excess electrons and stuff. Otherwise, this thing would just become fully charged with electrons, but I haven't been able to read anything about that. But I just assume there'd have to be something to pull away excess electrons. But nevertheless, the electron beam hits it. Where light is striking it, it's more conductive, so we get a higher current. Where it hits a place where light is not striking it, it's less conductive, so we get a lower current. And once again, our signal comes out that we can send to our picture tube to recreate the image that we are putting on the front of the tube. So the basic idea that Farnsworth came up with, allegedly when he was 12 years old, was to take his image dissector. As you remember, it took the whole image and just moved it around so that only part of the image went into the phototube. So Farnsworth's idea was to take the image, if we look at the front or back of the camera tube, we have our image on there, which of course is upside down. So we're going to scan across that image with our electron beam, creating a voltage that is proportional. So each time it scans across that candle, we get a change in our voltage because of the change in brightness, and send that off to the picture tube, the CRT, and have that scanned synchronized with the camera tube. So as we go across the top, we go across there. As we go across the next one, we go across there. As we go across the next one, we go across there, and on and on. And we end up basically, of course, much finer detail than this, although maybe his original one wasn't much better detail. In fact, the first thing he actually transmitted was just a vertical line on a card. But anyway, he repaints that image by synchronizing those two beams across. And a fairly simple idea, and like I said, he allegedly came up with this idea when he was 12 years old. When he was around 16 in high school, he diagrammed his whole concept after school for his chemistry teacher and explained what he was onto, and his chemistry teacher became his mentor. Although he didn't have a lot of electronics knowledge, I'm assuming, but who knows? He was a chemistry teacher, but he may have known his way around electricity a little bit, and encouraged him to keep developing it. Farnsworth eventually went to Brigham Young University, where he studied electronics and physics, and developed his ideas further, filed patents and such. And as a result, even though he was challenged by Vladimir Zworykin, he was credited with inventing the idea of television as we knew it at the apex of the analog television age. One thing that disappoints me about the video, The Secret Life of Machines about television, is they don't even mention Farnsworth. They give all of the credit to Vladimir Zworykin, who stole it from Farnsworth. Zworykin was working on a system, but he couldn't make it work. Then he was invited to Farnsworth's lab in San Francisco to see what Farnsworth was doing, because Farnsworth thought at the time that Zworykin was working for Westinghouse, which he no longer was, hoping that Westinghouse would pick up his idea and develop his television. Zworykin instead took his ideas to RCA, and they developed television further. And like I said, Zworykin was credited with inventing the iconoscope. But in the end, after many, many patent battles and court battles, even some of those after Farnsworth died, the courts determined that Farnsworth was the actual inventor of the idea of electronic television. So when you're watching The Secret Life of Machines about television, which I will link here, let's put a QR code up here for that. And I recommend you watch it. It's linked here. It's also linked in the page on TV at Vocademy. Recommend it highly. Very good video, good visuals. But just remember that it was actually Farnsworth who developed this and not Zworykin. So now we have the system where we have our camera scanning our image. We have some kind of electric signal going to a CRT that is presenting the image. Now we have to develop a system to make that signal go from point A to point B, synchronize those beams as they're going across, and actually make a working system to develop that television. So let's move on and see how that was done. First, we have to get that electron beam to scan across that cathode ray tube, whether it's the imaging tube or the display tube. So we have our electron gun shooting out the beam. We've got some magnets here. I'll show them as coils of wire to focus that beam onto the screen. And then we're going to have some more wires, electromagnets, around here to steer that beam right and left and up and down. So there's going to be magnets on the top and the bottom to make it go up and down, and I'll draw some on the side to make it go back and forth. So that's the beginning of it. We need to have a signal going there to make that move. So what we need is an oscillator. I'll just draw that as an amplifier with some feedback. What do you get when you give positive feedback to an amplifier? You probably get an oscillator. And we want that to create a sawtooth. It's probably going to be a relaxation oscillator, which we talked about way back in oscillators, which means we're going to have a curve that goes like that, drops down rapidly, goes back up and drops down rapidly. If we can capture just this part of the curve, that's going to be fairly straight, and so we'll end up with a pretty good sawtooth. Now, we could have a triangular wave. In fact, who knows? He may have tried that first, although it's a little harder to make. Let's say he did a triangular wave, and that would make the beam scan over and back and over and back and over and back evenly each time. And so if he had that scan top to bottom, use the other magnets to move that down, we would get a pattern such as this. And I don't know, he may have tried that at first, but eventually TV settled on using a sawtooth pattern. So it goes up and down rapidly, up and down. So as it goes up, the beam goes across, and then it rapidly goes back to the other side, then goes across again, then rapidly goes back to the other side. And we're not interested in what's on the screen during the back scan, as it's called. So actually, we need to turn that beam off. That's some of the complications of the electronics we'll talk about a little bit down the road. So in the end, though, we end up with two oscillators producing sawtooth waves. And I will put our screen over here. One is going to be the horizontal oscillator, which is going to produce a sawtooth like that. And that's going to make this go over, snap back, over, snap back, over, snap back. Then we're going to have another one that goes much, much slower. And that's going to go to the coils that make the beam move vertical. And so as that is going over and snapping back, it's going to be slowly moving down the screen. Over, snap back, over, snap back, over, snap back. And it's going to do this many times, so I don't have this to scale, but eventually this is going to drop down, so it's a sawtooth also, and it starts over again. So when it gets down to here, it's going to suddenly go back up to the top. And then everything starts all over again. So simple, easy peasy, right? Well, it's a simple idea to get that to scan back and forth like that, but how do we keep those synchronized? So we're going to have some method of synchronizing them. I don't know what the earlier methods were. They were probably directly coupled to each other somehow, because I'm sure it wasn't put into the signal like it was later down the road. But we got to keep these synchronized, and so there has to be some mechanism for that. There also has to be a mechanism to turn off the beam when it's going back. Turn it on, turn it off. Turn it on, turn it off. So there's going to be another mechanism. Maybe it's going to read the voltage or something like that. I'm not sure how he did it. There's different approaches, but we have to have some mechanism to tell it when to cut off and when to turn back on again. So it's probably going to have to monitor where this is here. Beam on, beam off, beam on, beam off, etc. And then down here, it's going to have to be beam on, beam on. Of course, it's going to say keep the beam on, but this one's going to be saying, well, I'm going to turn it off in the little intervals here. So they're going to work together to do that. Then it finally says, okay, now turn it off for sure while I jump back up here. Now, in modern systems, it does not jump straight back. It actually takes a few of these lines as it goes down. It's not instantaneous, so it takes a little bit of time. And so during that time, it's going to go back and forth a couple of times, but the beam is off, so that's no problem. That's done when this all is turned off and everything's going back up. It's called the vertical blanking part of the cycle, and it goes back up to start the whole thing over again. So we now have a CRT with magnets to move the beam around. We have these oscillators to tell the beam where to move, that go through amplifiers, to go through the coils of wire to change the magnetic fields, to make the beams go back and forth, and this one to make it go up and down as we've described. Now, I don't know if he ever used electrostatic plates to do this, but some systems, for example, analog oscilloscopes, tend to use electrostatic plates to move the beam, but it's the same concept. Instead of magnetic fields, we use electric fields, and those are built into the CRTs, and we still have to have the same oscillators and such, but instead of sending current to magnets, we send voltage to electrostatic plates. So it's pretty much the same idea. But modern televisions used magnets around the cathode ray tube to steer the beam around. So now we also need another system to synchronize the playback system with the recording system. So we have over here a cathode ray tube, crude drawing, but it'll work, with that photosensitive plate inside, sending electricity back there with the electron gun, sending the electrons to scan across that, and of course our lens to form the image on the tube. That has our oscillators, horizontal and vertical oscillators that go to the magnets to steer that beam around. Off comes a signal that goes through some magic and eventually hits another cathode ray tube, which also has the magnets around it, the electron gun, and now we have a phosphor screen here, and that electron beam goes to the phosphor screen, and we have the horizontal oscillator, the vertical oscillator going there to steer it, and the electronics coming in, and a bunch of magic going on in between, and whatever this scans over here goes over here. We have to keep these synchronized with each other. Early models may have had separate wires to go through to synchronize them, but by the time we got to TV, as I learned it back in the day, we had put information in the signal that's going from one side to the other to keep these synchronized and to make them work together. I'm not going to go into a lot of detail about that right now because we're just getting started about this. Just to give you an idea of how this worked, we have a signal going across and we have a certain voltage, whatever it is. I don't know what it is at the point. It's going to be somewhere, it's going to be pretty low voltage, maybe even lower than a single volt. But somewhere is going to be what's called the black level. That's not going to be our lowest voltage. That's going to be something above it. Let's say that's 0.1 volts is black. So if we go below that, it's blacker than black, when there's a use for that. And then we're going to have another voltage, which is our maximum voltage. Let's say that's 1 volt, and that's going to be white. So as these voltages change, we're going to tell the picture dark, bright, dark, bright. So as the electricity goes across, voltage goes up, it says to make this beam more intense, to make it brighter. As it goes down, it tells it to make it dimmer. And we have the signal going across. What we're going to start out with is first, let's get those guys synchronized. So here we have a signal going across just at the black voltage, and let's drop that down to 0 volts. So it's 0.0 volts. That's going to be, we'll call that our sync. And that pulse is extracted over here to our sync circuitry that synchronizes these. So that's how the two get synchronized. There's circuitry over here that inserts that synchronization, and then there's circuitry over here that extracts it out, and that tells these oscillators, both horizontal and vertical, to synchronize with each other to make this whole thing work. Okay, so after that sync signal is sent, then our scanning process is going to start. And so this is going to be the first time across the screen we're going to get, let's say we're looking at that candle again. So here's our picture that we're scanning. And so first few times we're not going to get anything. Let's say we're at the point where we're going to get that candle flame. So we get black, 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 and then some white, back down to black, and then we finish that particular line. And then when it's finished, we're going to get another sync pulse. So that is what's called the horizontal sync. And that goes for how many lines we have to go. In the US, television theoretically had 25 lines from top to bottom. It really didn't. It really only had, I forgot the exact number, but a lot of those lines were actually part of the vertical sync process that we actually don't see. So I forgot the exact number of lines. I'll put it up here. Those are the number of lines that were actually carrying picture information, but the rest were not. But anyway, finally, after we do this a number of times, we repeat that over and over again as that scans across and gets the picture, sends it over. And of course, this is synchronizing both at the same time, creating the picture over here. We eventually get to the vertical sync. So we'll say we just finished our last line, time to go up. So our vertical oscillator has come up and now it's started on its way down. So it has to tell the system that it's going through the vertical now. So what it's going to do is send a whole bunch of these horizontal syncs. And in the modern system, it sends a certain number and then it changes the phase. And probably not drawing it quite right. Here's a picture of what that vertical sync looks like. And that is picked up by the system here to tell it, okay, let's get our oscillators in sync, get ready for the next field. And then finally we get the last horizontal sync. And then we get our image information. There we are going across the candle again, horizontal sync. And so we do that again and again. So that's how they were able to synchronize the two systems. Now back in the early days of television, we had to have all sorts of controls to help these syncs stay together. In an old TV, you had a horizontal hold and a vertical hold, and usually they'd hold up together, but sometimes it would start rolling vertically, which meant that the vertical oscillator was getting out of sync with the one in the transmitter, and so the picture would start rolling up. And you see this big black bar go through, which was the darkness during the vertical blanking cycle when all that stuff is happening. In fact, you could actually see little lines on the screen, which were actually how those showed up on the screen, and you'd see a whole bunch of some lines and other information. And later, when closed caption was put in, you'd see the digital information for the closed captioning in there. But you get these black bars that would start rolling up or down the screen. You have to go and adjust the vertical hold to get that to stop and get that locked in. And then you also have the horizontal hold where you get to get the pictures going sideways. When you start going off to the side, you have to adjust that horizontal hold to get that to lock in, so you didn't see a black bar going across as your picture slid from right to left or left to right when they got out of sync. But toward the end of the analog TV's heyday, we had some systems that locked in so well that we didn't have to have those controls on the TV. Now before we finish off, I want to add how they added color to television. That gets rather complicated, but I think I can simplify it. And I'm not going to talk about how that was broadcast because that's a whole new complication we'll talk about down the road in communications. But just how did they put color on top of this luminance only signal that they were able to develop in this way? Well, to make a long story short, they used 3 cameras with filters on them to get images in red, blue, and green light. These signals were combined in such a way that they created a sine wave at 3.59545 megahertz. Why do I remember that number? I don't know, but I do. This frequency was chosen because it would create the least interference in the broadcast system. So we're well into broadcasting before color was invented. But this could have been done with other frequencies had it not been for the broadcasting. So we just not worry about that. It's just a sine wave at about 4 megahertz. So the next thing we do is take those 3 colors coming from 3 cameras and divide them into a circle. And so now we have, let's say, red, blue, and green. So here at 0 degrees is going to be fully red. So red right in the middle. As we get over to here, we're going to be getting, see, red and blue together. We're going to get into magenta. And that's going to be over at 60 degrees. And then over here, we're going to get into blue. Here at 180 degrees, we're going to be into blue and green. That's going to be cyan. And then over here is going to be completely green. Then over here is going to be between green and red. That's going to be yellow. So on your television, you mix red and green and you get yellow. Okay, so now we have all of our colors in this wheel. We can create any color in the rainbow by going around this wheel. So what we do is take the information coming from those three cameras, convert it into an angle, and we make that the phase angle of this sine wave compared to a master sine wave. So there's a master sine wave that gives us our 0 degrees, and then we make our color a phase shift. So now what we do, let's get this out of the way. This gets pretty complicated. But now we have our horizontal sync. And then instead of sending just a voltage, we're going to send that sine wave. And as we hit a light spot, the whole thing is going to be shifted up and then shifted down. So instead of just having a little blip there for the candle, we're going to shift that whole thing up and down. So the mean level of this gives us our luminance, but then the phase angle of this compared to our master is going to tell us what color it is. And that goes to the other end, and there's circuitry to pick that off. In the receiving end, there's a crystal oscillator at 3.579545 megahertz. And that is going to be the master oscillator at that end. So we have a master oscillator over here to create it. We have another master oscillator over here to receive it and to tell us what the phase is. So all we have to do is make sure that this master oscillator is in sync with that master oscillator to tell what the phase is of that signal to tell us what color it is. How do we get those to synchronize? Well, I left a little something out right here. They send 8 to 10 cycles of the master oscillator there, and that is extracted from the signal and synchronizes the slave oscillator over here to make those two oscillators to be in sync. So that's how they added color to the signal. Now, as far as for color on the receiving end, there are different approaches. In fact, there are projection systems that use 3 different CRTs for the projector, but what was developed was a way of having 3 electron guns in one CRT. So here's our front end. Looks a little more shaped like a modern TV. There's 3 electron guns, all shooting at the screen. And between the electron guns and the screen is a shadow mask. Here's a picture of one, just looks like a little screen, doesn't it? Thousands upon thousands of tiny little holes so that each gun only goes a certain direction. So here's the shadow mask, and one gun fires through and goes through at that angle, another one comes through at that angle, and another one comes through at that angle. All we have to do is have 3 different spots. So this is the red gun, the blue gun, and the green gun. And we put red, blue, and green filters. Let's see, red filter, blue filter, and green filter, so that the phosphor lights up and we see when this gun is shooting, we see red, that one's shooting, we see blue, and that one's shooting, we see green. So that is how the color CRT was made. So that's about all I wanted to say about television at this point. We're going to talk more about how television worked in the communications class when we get into television broadcasting, but that in a nutshell is how television was made. I recommend that you do watch The Secret Life of Machines. There's a link to it right here. The video on television, although they do not even mention Philo Farnsworth and give all the credit to his work, and it's still a very good video and explains a lot of these with a lot of illustrations I don't have the means to create. So that's the basic idea of television as far as getting the signal from one end to the other. We'll talk about broadcasting down the road when we get into communication circuits. So I hope you found this useful and informative, and if you did, as usual, please give me a thumbs up. Really helps the channel, and don't forget to subscribe. Hit the gray bell when you do so that you get notified when I put up new videos. And if you want to study electronics technology and perhaps become a certified electronics technician or just get a jump start on your studies in electrical engineering, you can go to Vocademy.net and take my free course. And of course, these videos are sponsored by you. I could not do this without your support, so to help me put these videos up and to keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support, or to make a one-time donation, you can go to paypal.me/Voced, VOCED. As always, a big thank you to my patrons, my one-time donors. I could not do this without your support, and thanks to everyone for watching.